There you go. Who wants to start?
Give us an introduction first.
I could give a quick update. So let me share my screen. Find the doc. So yeah, okay. So I looked in Puma 5.0 experimental features suggested by Camille. So there were two of them applicable to our like memory situation, memory story. And first was Nakayashi fork. The idea is, I think Camille doing similar stuff without Nakayashi fork, right? The idea is to run GC a couple of times before forking into worker on the master process, and then doing compact. And in the end, like it was giving me some advancement on memory. Like I was looking into 90 megabytes, sometimes less, depending on like experiment I was running to, and it's still worse than single mod. So like my outcome out of this experimental feature is that single mod is probably the way we will be going to, because like, but what is good about Nakayashi fork? It seems like safe enough.
Sorry, Matthias. Yeah. Okay, we are recording, right?
Yes.
Yes.
Okay, sorry.
Yes.
Yeah. I think that we did not.
Yeah. So.
By the way, Alexei, I did the same thing, right? You're aware of this, right? Just so because we said we want to make sure we're not overlapping our work.
No, but I not aware. What do you mean? You did the same thing.
Okay. Well, we talked about it yesterday. I mean, I looked into compaction, right, for a whole day.
Yes.
So I did the same thing. Like I looked into just before we fork into Puma workers, what does it buy us if we run a compaction includes two major GC cycles actually. So
yes,
GCing and compacting right now is the same thing.
You're talking about this. Yes, I know this. I wasn't doing like any deep research on the Nakayashi fork. I just enabled it, measured it, and as I mentioned, like you and Camille, you are doing the same, but let's say manually. But this one is included into like setting of Puma.
Oh,
so
it's like a special version of Puma.
Yeah. No, not special version. Just a setting. You enable it, set Nakayashi fork true, and on Puma 5.0 it starts doing the thing. So it gives an advancement like expected, but worse than single. I also looked into fork worker. The idea is to not use master process in traditional way, but fork from a first booted worker, and then maybe refork from zero worker into another workers. So it also was like minor difference in my experiments. I was running it in idle, warm-up, GPT. It was like the difference comparable to amount of USS memory of the process, like less than 100 megabytes. So I didn't really look into Heap because I wasn't able to get to it yet. So my thoughts after it that I think we will stay with single mode because like.
So I have a question about the reforking. So what is the idea here? Is the idea that you warm up the worker with some requests and then fork? Because like if you refork straight away, then I don't see what the point.
No. First you refork straight away, but then like after running like let's say hitting 1,000 requests on zero worker, you will kill every other worker except zero worker and reforking. So you're doing this on a general basis, like after some amount of requests.
Ah, I see. So like only you keep reforking. Worker, or the first batch of workers is forked from master, but then any other worker that will fork in the future is forked from an existing worker.
No, right? Kinda, but they call it a bit different. You see, there is this picture. So you basically load first worker and forking zero worker, and then forking from it a first worker. And then these are most heavy workers. So you're not using master in traditional way. You're kind of starting to fork from zero worker. And then you keep killing all other workers.
What is the zero worker? What's special about the zero worker?
It's basically master. It's basically master.
Yeah, so what's the difference then to just forking from master?
I don't know. They call it zero worker. They don't use, let's say, master in this scheme.
Well, who's they?
Puma.
Okay, but I mean, there must be a reason why it's suggested to do that, right? So what is the selling point here?
I think basically use one less process, the selling point, how I see it.
Doesn't it use one more process? Because you have master and the zero worker now.
Yeah, but you're not loading everything in master, right? I believe, maybe I don't understand this, but I believe master is just for orchestration here. It doesn't like doing the same as master in, let's say, typical master plus worker setup. Like in typical master plus worker setup, master is loading whole application, right? Then we fork into workers. But here master is very lightweight. So while I was observing, it was 40 megabytes top. So all the preloading happened in zero worker. So master wasn't doing anything. It was just orchestrating stuff.
All right.
So zero worker was our kind of master, and then we forked from it. But after some time, we could kill our other workers and again refork from zero worker. So there is obvious gain. We don't have heavy master anymore. But as I said,
I see. Actually, sorry, like it says it down here what the benefit is, and I think that's why it doesn't benefit us, is because it says here this command can improve memory if you don't fully pre-initialize, which is what we do.
We already start very heavy. Very fast. So I didn't see a point.
So I suspect in this setting, when you enable this config, it probably does not preload the app. That's why your master is so simple.
No, it doesn't preload the app.
Yeah. Okay. Yeah, that's a big difference.
It's not compatible. And I also
like those master does not preload the app.
No, it doesn't have preload the app. It has. Let me check it.
I mean, if it would, then there would be no difference.
No, it doesn't preload up. Yeah, as you could see. Yeah. It preloads up, but into zero worker, as far as I understand. So let me check. Similar, yeah. So what I see, even before hitting the application with the first request, unless somebody else is hitting the application with first request on the background, I saw that zero worker is become quite heavy.
Yeah, I mean, so I think I understand now. So what they're saying is, so what we do currently in a traditional approach is we preload the app on master, but the master never serves any traffic, right? So the master is basically idle outside of orchestration.
Yeah, and it could not.
So when you
incorporate new
right. So if you start a new worker, you always fork from like a clean slate, right? You always fork a new worker in this model will never have pages loaded that you might have to load to actually service a particular request, right? Whereas in this model, the master does not preload the app, so it remains super lightweight and it still only does the orchestration work. But this zero worker is an ordinary worker, right? It serves requests. So if
it could have more information that we could.
Yes, you will have. It will be more representative of what the application will do, but it will be much less useful for those applications that like preload the whole app anyway, right? Because it's actually it depends on what. I think we never really. I don't know, Camille, if you ever looked at this in detail, because preloading the app, I don't actually know what exactly that entails, because clearly it does not. It does not mean that everything that could be in memory upfront is actually in memory upfront, right? Because we can see that by just if I go ahead and like just after forking, if the first worker or the first batch of workers goes live and I send a single page request, right, to the front page, it will start shoveling more data in memory, right? So
but
clearly,
I think like I wanted to check that if it's actually are we loading more sources afterwards, but. Like I think that like we need to be aware of like two things. Like there is like an actual loading of the application. I mean the code in the code base and like the classes, but there is also like the initialization of the application that happens on the first request. Like we lazily init some of the variables, some of the configs and things like that. And that's gonna happen on the first request basically.
Like, but you're not talking about initializers, right?
Sorry?
So you're not talking about initializers, right? What kind of initialization?
I'm talking that we have parts of the code base that are lazily init, like strong memo mines, for example.
Maybe in metrics, right?
Oh, yeah,
like all this kind of.
Yeah, I see what
when you first time hit this piece of the code,
yeah,
it's basically lazily initializing. And I'm just curious, like, do we load like some pieces of the code because of that are not preloaded in like the regular way and like are auto-loaded when you request the part of the classes that are not yet referenced? And the second one is like how many the strong memo mines happens that may like impact our memory structure that gonna like impact copy on write as well. So I guess this is what happens after the actual preloading. And this is why this rework fork actually is beneficial, because it ensures that we hit these parts of the code base basically as well.
So Alexei, this I don't know why Nakayoshi fork is such a like silly name, but so that is I don't know what it's supposed to mean. But like, so this is not the same thing as this reforking model.
No. They're two different completely features. Yeah, and they're not compatible as far as I know. I wasn't able to run both Nakayoshi fork and fork worker and see the results. So maybe I did something wrong, but I wasn't able to pair them up. Yeah, so, but like my outcomes from this, that probably single mode is the way. I mean, it's much better. It's like more than 100 megabytes better than what I see of any of these experiments. And yeah, I don't really think I could do something more without looking at the heap at this moment. Like, because these are just not like fully proofed experiments, because I just run it, I just observe the graphs.
But is the performance the same? Like because I mean, we talked about it a little bit yesterday, but I feel like we're comparing apples and oranges there, right? Because we're saying we're basically saying, well, a single node deployment consumes less memory than a 3-node deployment. But yeah, well, of course it does, because you have like 2 less processes. I mean, that's not really surprising, right? So the question is, does it perform equally well?
So Matthias, like performance will be worse, right? But this is kind of like the trade-off that you are like saying. It's like, I guess like it's about like the scaling, like how much CPUs you expect on the 2 gig instance, and how beneficial is using the cluster mode, which is really like for the multi-CPU installs. So I guess it's really like about the RPS that we intend to support on this mode.
Yeah, that's exactly what I'm trying to say.
It's kind of like the trade-off. You might be trading to like run like more efficiently, but like slower, but still like have this threading capacity. I would kind of assume that like on the this 2 gig instance, you would kind of expect to have 1 or 2 virtual CPUs usually. So I would say that this is mostly likely like what you're expecting. The case of the Raspberry Pi is probably different, because the Raspberry Pi has 4 vCPUs. I mean 4 CPUs, which are very slow. I don't know, like probably like.
To be honest, when I was looking at the GPT, it wasn't like gravely worse. More tests failed, but it wasn't like, let's say, it was like 2 seconds instead of 1 second, like, or 1.5 for a failed test. So I found this acceptable on a single mode.
And I think that weren't the performance tests we ran, they were a little bit unfair, right? Because we were giving it more traffic than that kind of architecture is actually meant to support, right? If I remember.
To be honest, I started to run 5 seconds, not like 5 seconds, but 2 RPS. I started to run them because it's just faster. Yeah, it was just much faster for me to see under some load, because my point was not to run performance test itself, but to warm up, let's say, some endpoints and to load some data into memory. So I was mostly running on 5 second 2 RPS just to go through all this.
Okay. By the way,
endpoints. Camille, I have like a short question for this. So what's holding us from updating to Puma 5? Like, except the fact that I noticed we use our fork, right? Our own like GitLab.
Nothing is really holding us.
I mean, it just came out last week, right?
It's like ensure that this works properly, and like we configure on this aspect, because like this, we are using our fork because the older version didn't have like this my fix to the performance, but 5.0 has this as an experimental feature. So you can still configure that. So nothing really is holding us. It's more like the time to ensure that it works properly.
Okay. So I think that I will probably, I don't know, pair with Nicola and Matthias to learn more about Heap today. Because I think that like, even if to continue with Puma, I should, at this point, I should start looking into the Heap difference. I mean.
So I'm kind of like wondering, because like I'm kind of set on the single mode for this very small instans, but there is also this refork thing. Like I just wonder that maybe as a trace, this is something like for us to figure out, maybe not this week, but maybe in the future, to actually understand how much benefit it brings us when running in this cluster style.
Well, what I could do is I could set an aggressive refork, let's say every 100 requests, and run GPT and see how the memory grows. So if it will be at bay, like much more in bay compared to, let's say, less aggressive refork, then it gives some difference.
Yeah, I think the key point here really is that the main benefit you will get from this, or will get more benefit if the zero worker is representative of what production traffic would look like, right? So you need to warm it up, and
yes,
this might be across like a number of, So I don't know.
We need to run a quite long.
This. Yeah, right.
Maybe a quite long GPT with more requests and more aggressive reforking, like even if it like hits performance, just to see how it affects memory. I could run it really fast.
It's also, I don't know how the Puma authors would see this being used. So because I keep thinking like for .conf, for instance, for us, right? We have a lot more options like with how we roll this out, right? So we could, because you can do like rolling deployments, right? Where you deploy a new worker and then you let it warm up in the background while you have your old worker still servicing traffic, and then you might switch over to the new one from which you then fork. But I don't know how, like in environments where we don't control how this should run in production, or where we have no idea basically what kind of traffic we will service, this might be really hard to tune, I think.
I'm kind of like curious, like how this reforking, how stable is that, and like first, like how much benefit it brings, and like what like side behaviors it has on running on the production. Because like I think that idea is super clever, but it's like kind of different and more risky compared like to how we run before. So
yes, they mention it, that it's like much more experimental, let's say, than Nakayoshi fork, because while Nakayoshi fork is just straightforward and safe, run GTs, this thing could cause some side effects, as I mentioned. So
yes, and like Nakayoshi fork is pretty much safe, really, like one, I guess, because like it's pretty straightforward. But I'm just kind of wondering if there is like some way for us to have the refork benefits without doing refork. So like in the current model.
I see what you mean.
And this is like what I'm like also interested about, like
maybe on hook.
And this is what I'm kind of like trying to see to like this. What is being loaded afterwards? What is being initialized afterwards? What happens between this time that like you fork and you process a single request, and like there's this spike in the memory consumption? Like what operations do happen during that time? Can we somehow make it happen before, if it's possible? How much it would bring a benefit? Because if we can somehow like make this work without the reforking, it would actually be probably much safer way to implement. And maybe we could save like another, I don't know, 50 megabytes.
So ideally you want a master before firstly forking into worker to do some job, right? Like to imitate something like either loading additional code, which will happen anyway in first request, or serve something, right? And then only start forking to work.
Yeah, so I'm kind of really curious, like what happens And actually, like this can be done like with the execution profile probably. What happens between like our fork and like processing the request, pretty much like any request. And actually, I'm kind of now thinking that we could really like do like execution profile out of that. What is being executed? I mean the flame graph maybe, but the second one like execution profile, what methods are being hit during that time, like of between like fork, when you fork into new process, and like then you execute like the first request.
Okay. So maybe something to look into. Let me add this to the doc. So I think I finished with my update. So I just add what Camille mentioned into the doc. So I don't know where to add, like, and okay. So who is the next? Camille?
Sure. So I guess like all items that I look at, I look at the 20 RPS. It's like pretty nasty for running in the 2G, because one of the reasons that I kind of like got to understanding why we I see like pretty nice like the Puma and side key memory usage over time, but like a very steep increase in the swapping at some point. And I noticed that it's due to like to Git processes running from the Git DALI. It's basically spin ups like 20, 30 Git processes because of the unlimited concurrency, which kind of leads me to the conclusion that in this small instance, we should limit like the Git concurrency as well to ensure that we control like how much is being spin up. And why it is bad, because these Git processes are in the GPT, they are for like the big repo, and they consume like a ton of memory. This memory is being shared, like because like the Git repo is mmap, but it's still pretty like evicting to the application.
But I thought, is this because of rugged? Because I thought we use GitLab, which should be single proc, right? And just use
no, like GitLab has like actually has 3 ways of accessing repo.
Okay.
And like getting data from the repo. Like I'm not talking about the rugged. Rugged is something to kill at the soonest possible moment. I'm talking about the GitLab. GitLab can open repo directly in the Go process using libgit tool, and they implement some of the functions. They have legacy way of accessing Git repo, which is through GitLab Ruby, a side process that is running that they communicate with. This GitLab Ruby also opens, but in the Ruby context, the repo using libgit tool. And there is also, for some commands that are hard to implement with libgit, we just shell out to the git command line, basically. And,
okay, wow.
And I saw like these shell outs to be like, for some cases, for some requests in these 20 RPS to be like pretty evicting, because we're gonna spin up a ton of Git processes basically, and it's
this
gonna
sounds like the image scaler problem all over again. Remember,
sorry?
because we had to put kind of a rate limit in place for the image scaler as well, because we just fork on request.
Yeah, so it's actually the same problem. I mean, GitLab allows like to limit that, but by default it's unlimited. So I'm kind of thinking that if we would limit that to like to some same number, maybe 2 or 4, or this 2 gig, it would kind of like, let's say, behave properly.
I mean, the problem there is with image scaling, we have a clean failover path, because we can always go back to serve the original image. But what is the failover path with Git? You can't just drop the request on the floor, right? Because you still need to do that work.
Probably,
you would
no?
have to,
probably it's
queue it
gonna wait for some time, which is like the deadline defined. And like if you wait, go beyond this deadline, it's gonna basically fail.
So it's a queuing problem then, which comes with its own problems.
Yes, but like I guess like I think it's acceptable like to have limits how many concurrent operations.
Yeah.
And like it's acceptable that it's just like this small install gonna have like lower capacity. So maybe it's kind of like after Alexi comment, like maybe 20 RPS is just like overkill. Like we should be testing maybe 2 or 4 RPS, which is like more realistic.
Yeah.
Even like the amount of the resources that is available for you.
And how much memory does each get process consume? Just like roughly, do you remember?
It really depends on the repo that you're opening, because they are mapping the repo, the process, and so like system is gonna need some memory buffers like to do this mapping, and also there's some additional processing. But Git is in generally very efficient, but like still mapping requires like some memory like to run. And if I recall properly, like the very big memory usage by the Git process is something that is, in general, our problem, basically. That it kind of creates a spike of the memory usage in some circumstances. And like we have no way to limit how much memory is being used today. And I think that there are some issues already for that in like our, maybe not in our tracker, but of the Gitari.
Yeah, thanks for sharing that. I had no idea it worked that way. I was kind of assuming like that, oh, nice, we have Gitly and, you know, everything runs single proc, and apparently not. It's good to know.
So then I look at the GC params. I link like the defaults, and I kind of try to be very aggressive. Like I noticed that like being very aggressive is actually beneficial for the memory usage because it's much smaller. However, I still was unable like to see the thread pages being in the GitLab process. So I may continue looking at that. I noticed that on my like linings when I was running site, but I was not noticing that on the GitLab process. So I'm not sure yet. I need to investigate exactly like if it's due to the pages that maybe are fragmented, or maybe it's due to some other reasons. I don't know about that yet. I also like, which is kind of like, I think it's very close to like what you Matthias did. I kind of like look at each object of the string and like look at the frozen ones, unfrozen, and one that can be deduplicated. And I noticed that like we can really like deduplicate about 25 megabytes of the strings basically in the Ruby processes of GitLab, which seems like pretty big number. I just didn't yet found like the easy way to deduplicate everything. Like I can iterate some objects and like deduplicate in these objects, but some objects are frozen, so it makes it impossible to deduplicate them. I mean, I look at the Ruby GC code, but it's pretty complex. It's like 12,000 lines of the code. It's not really straightforward. So I didn't found a way like to, let's say, update all the memory references of all underlying structures to perform this kind of deduplication in the native. I'm kind of like thinking that in general, like the GC deduplication of the strings could be really like a nice addition to the Ruby, because like it's actually free memory to reclaim without any performance benefit, without any impact on the application running at all. And like it actually is kind of linearly with the big application, the bigger the application is. And like Matthias, like you said that like we are allocating how much like of the Ruby memory, something like 150 megs or something of the Ruby heap, or is it more?
It kind of depends on what you look at. That's the main thing that kept confusing us. So if you sum up, so I looked at two things, like that was 2 days ago or so, which was summing up object space each object, and that came down to I think 190 megabyte for me. And then I look at the GC stats as well, and if they can sum up the number of allocated pages, which might not be full, right? So that doesn't actually, so that's kind of an upper bound. So it's an upper bound for the currently used, but it's actually representative of, or it should be representative of RSS. So if you multiply that with the page size, which is 16K, I also got around that number, like 150 to 190 megabyte, which was well below the actual memory used. But if you look at reports from, I think, what was it? Was it Derailed? I think, and Nicola, you spent some time with Derailed. Derailed like was reporting 900 megabyte use or so. So it must be looking at, I don't know yet what it does, but it must be looking at other stuff as well. So, and Heapy, I think as well, it was considering, I don't know, like what we can maybe look at what they do under the
RSS for Heapy is showing 800 megabytes.
Yeah, that makes total sense, because that's what we were seeing in like idle memory for the Puma worker.
So then I also look at this instrumentation. It was like commenting like one line of the code basically, and it kind of gave me like some idea that just removing that alone should give us probably about half a meg of like reduced memory usage, like basically for free. I also look at the Prometheus client, and I like kind of remembered exactly how it is behaving and how it's implemented. And basically Prometheus client can also quite significantly increase memory pressure over application run. And I'm just unsure, maybe this is also one of the reasons why this usage grows over time and why like it increases the initial memory usage, because like different types of the metrics like histogram counters, gauges with different aggregation types, each of them need like an individual mmap file basically, which is owned by the process, and the current mmap minimal mmap size is like 4 megs. So it means that we may not use the all pages of that, but it means that over execution time, if we gather a lot of metrics, we're gonna be actually kind of linearly increasing amount of the mmap memory, and we may be kind of requiring a significant space on memory buffers, which kind of reduces the amount of the memory available to the process itself. I didn't get exact number like after disabling Prometheus, but I think I saw like something around 60 or 80 megabytes less when disabling Prometheus metrics. So I guess this is like another venue for us like to really investigate our Prometheus integration, because I think it can be pretty big sink of the memory usage in the processes.
There was an outage even, right, a couple of months ago, where we were running out of memory in production, and they tracked, like there was a super interesting, I think I floated it in the channel back then, like Stan did a super interesting like debugging session where they looked at a raw, like a core dump basically of what was going on in one of these processes. And it turned out there were like massive strings of Prometheus metrics we were trying to push out through the exporters, which consumed a ton of memory. And they made a change, like there were, I forgot the exact reason why these strings were so large, but apparently there was like a bunch of information in that we didn't actually need to export, so they fixed it that way. But maybe there's still, more opportunity to look at. So maybe that's exactly the same reason you're seeing that.
I'm not sure, but like for example, if you have like very long label, I don't think that we really sanitize the label length. So it's very likely that it may have very long labels, which is one thing. But the second thing is like the way how it's written is just, it's kind of like linear growth over time, and it's like not really optimized. So I guess this is something really like for us to look at and figure out like how it can be done better, more efficient, or anything, like, because like I think like we are kind of at the limit of the scaling of the current Prometheus metrics. Like we can, like even scraping of these Prometheus metrics takes, I don't know, on the GitLab.com, something around 5 seconds basically. So it's pretty extensive. It's pretty, I mean, it's very, very optimal in the way how it's written. But I think due to the amount of the metrics that we have, we need to figure out something basically better, different approach to this problem to ensure that we don't hold that in the process memory. We maybe somehow accumulate that metric somewhere else. I'm not sure like how to approach that, but I think that this can be really a big thing of the memory usage that increases over time. That like we basically store like multiple metrics per single controller as well. So I think this could be also one of the reasons why we see like pretty, let's say, reasonable usage of the memory on the Ruby process, but there is a lot of other memory leaking outside. I mean, not leaking, it's kind of like being mallocked or like done outside of the Ruby. And Prometheus client today is written natively in the C. So it's a mapping, it's pretty efficient, but like it's not, you cannot recycle that memory. That's the problem as well. And it actually has pretty severe consequences for like the long running processes where like it increases memory like kind of like into infinite.
Okay. Yeah, cool. Thanks.
Matthias.
Yeah, let's. I guess I can do it together with Nicola because we work together most of the day. Yeah. So what we wanted to drill more into the heap usage of the Puma process in general, like what's going on, and so what we spent most of the time on was looking at a heap dump generated with object space dump all. So this actually gives you a full account that even includes like memos and internal Ruby objects like VM objects. So it's fairly complete. And also if you look at the cumulative size of these reports, they are much closer to what we were seeing in terms of our RSS. Not always, right? There were some discrepancies. Because it also depends, it's a bit tricky because you need to trace allocations first. And depending on when you start tracing allocations, you might not actually catch, all the requires or whatever. You basically need to do it like before your app does anything. So it wasn't super easy to get a full account. But yeah, anyway, so by default, this is just a JSON dump, like a JSON blob, basically. It's fairly readable, but it's like not aggregated. So there's a tool called Heapy that we use to run over that data, and it gives you like a interesting breakdown of like where memory is allocated. It can trace it back to files as well. So that's all updated in the issue. We then it took a while to get there to actually get this. I think today we need to spend a bit more time in actually like looking at this data. And looking at all these individual reports because there's a ton. Like Nicola updated it all in the issue. There's like a dozen different sections that we can try to wrap our heads around. We then proceeded to. So one thing we observed was that there is a big chunk of memory that is reported as just anonymous pages. So it's just like in RAM pages that are not backed by files, right? So, we don't really know what's in there. And one thing we wanted to find out was to what extent do like things like shared libraries and like external code that is not Ruby contribute to this. So one thing we did was we looked at the memory mapping data for running Puma worker. And that is summarized in a spreadsheet that maybe I can quickly show that just super quickly. I mean, there's not, unfortunately, there's like not a big takeaway, but maybe it's interesting to see.
So like, Matthias, you are saying that like we have like a little of the memory mapped files or something like that?
Yeah, a very tiny amount only. So this is the raw data from. By the way, we ended up changing the. This came from the VM running Omnibus, but we changed it to single mode because it was quite difficult to reason about like page sharing, all that if you have 3 different processes to look at. So we wanted to see first, just in terms of what the memory layout is, we wanted to look at a single process. So this is now from a single node, a single worker, Puma. And you can see this is, I just created a pivot table based by, or maybe I should say first, so this mapping will tell you, so blank basically means it's not mapped backed by a file, so it's just directly mapped memory that is just in memory for that, in RAM for that process, and this is the aggregation by the mapping. It's not always a file. So this blank here is basically the sum of all the memory that is not file backed. They all end up kind of up here. That's just the total. But yeah, you can see like the vast majority like is not backed by a file. But I think it was still an interesting exercise to see what kind of contributes to memory. But all of this is like quite tiny, so it probably doesn't make sense to look at external libraries. But yeah, it's, you know, if have a look at it, it might be interesting to see just like what there's a ton of stuff actually that we map into memory that is not specifically Ruby code. So I thought that was interesting to look at. What else? Yeah, I mean, that's pretty, oh yeah, we also then were wondering, okay, if there's some discrepancies between like what object space tells us is being allocated on the heap, maybe there's a ton of like mallocs going on that are not reflected in these reports. So we wanted to see maybe there's a way to understand what calls malloc, or from where do we call malloc, and how much memory is allocated that way. We have no idea if it's going to lead anywhere, but so we looked at jemalloc again, which is the allocator that we use, and it has a profiling companion tool called jeprof. So you can actually, and we compile jemalloc with profiling support enabled, which is good. That's just configured like that in Omnibus already. So we created a profile dump. You can have a look at that in the issue. It's just like totally illegible by default because it does not like the symbols, like where this is being called from, is just I think an address in memory. So it's unusable. But apparently, and we didn't get around to do that yesterday, there's a way to unwind these and map them back to the actual symbol that was used. Apparently that's preserved or help that's preserved somewhere. So I'm hoping that if we try that again with this deck, there's like a Igor found this at the end of the day. There's like a parameter you can run it with dash symbols, which should reverse the resolve these the raw addresses to a symbol table, so that we can actually see what the method, I guess, or the function was that we were calling there. So maybe it'll help. I don't know.
I tried running it this morning, but it's stuck.
It's stuck. Okay.
Yeah.
Yeah, so the problem is these heap dumps are massive, right? It's just like, it's a sampling profiler, and you can tell it the interval. It will like sample, you know, every so and so many like kilobytes or megabytes or whatever you tell it, but it's quite large, you know, it produces large files. And a lot. I think the first heap dump we took was like 20 files or something. Yeah, so that was yesterday. Well, okay, we can talk about today later. Well, I guess that was it, right? So we can talk about today. Should I just start then? Then someone else can take over.
Yeah.
So what I was thinking is I still would like to understand like where all these big differences come from. I think it would help us maybe to understand, in what sense Heapy and Derailed seem to give us a more complete account of the memory spend. So what is that? Like, what is that difference between this and what we were seeing when we were looking at GC stats and object space results separately? I think that would work. You said you tried this already. Do you think it's not worth spending more time on, Nicola?
No, I still think that we need to figure it out, like, and maybe detect the potential offenders. So.
Okay. Yeah, I mean, maybe we can time box it. Maybe, yeah.
Yeah.
I still suspect it will be difficult to work with the result of this, but yeah, who knows? Yeah, then I mentioned already, I think, so we have a lot of data collected, but I don't know about you, Nicola, but I haven't spent a lot of time yet on actually looking at all this stuff, because there's a lot now. We have all these derailed breakdowns, and I think there's like the Heapy breakdown somewhere as well, which could be interesting. So I think it would be good to start maybe summarizing somewhere, because we have a lot of these like raw data dumps in this issue, and it takes more and more time to scan through all this stuff, and it's a bit overwhelming. I think maybe we should start kind of wrapping this up a bit and try to draw conclusions or highlight the interesting bits, maybe in a separate place even. I don't know. So I think that's something we should spend some time on. Yeah, that's all I can think of for now.
Yeah, I agree with you. Like, I don't know, with the jemalloc dumps, I will try just to fix the library and see why it's stuck. So I will really time box it to see if we get some readable data, but I will really time box it. But in that issue, as you said, we collected like a lot of data from different tools, like, so we should start like trying to get some sense from those data and see, can we do something about it? Or because I think we collected a lot of things, like there are a lot of lines that could be expanded in that issue, and we didn't spend much time of like trying to understand those results. So it's something that I will try today.
Yeah, sounds good. I mean, it's good that we have a ton of data now. That's a good start.
So we can probably split somehow later.
Yeah, okay, that makes sense.
See.
Yeah. All right, I'm gonna stop sharing my screen. Who's next? Just about.
Well, I think that I don't have much to add to the Matthias update. So,
okay, so no, I was thinking because did we go through the today stuff already?
Yeah, okay. But I have a question. So I wonder, should we use like Camille's settings already in running some benchmarks and so on?
They are super aggressive, really.
So you don't think it worth it?
I think like it shows one aspect, like the settings are not the best, and like we need to find settings that are tuned to GitLab, but my settings are not tuned to GitLab. They actually cause performance issues. It's rather like I think this is like the point for the future. Like we can gain a lot if we tune the GC settings, basically. I just don't know yet what the settings are there.
Got it.
So like the only, I guess, thing that we may use is like Puma single, which is like, I think like predictable. Maybe like, I don't know, disabling Prometheus metrics instrumentation is also like kind of predictable. Like we lose some observability, but like, I mean, like it kind of reduces memory usage to kind of like, I mean, like if you disable that Matthias and Nicola, like you should see slightly different pattern, but then you kind of know that this is due to the Prometheus basically. And it's disabled. So this can like remove some noise from your testing as well.
I also found an article on deduplication. So I'm curious by Sam Saffron, but he mentioned some limitation, like, for example, if we get like a method on a string, it creates ivar in Ruby and won't allow us to duplicate. Do we have the same limitation, like in what you, Camille, mentioned? And also he mentioned that, for example, tainted strings, which I didn't like have experience with. So he mentioned that there are a lot of duplicated strings which are tainted. So is it kind of in the same area you were talking about, or is it different?
Yeah, so actually, like if you look at the issue that I created and I posted some results, there are actually like plenty of the strings that could be dead up. And like the strings that have ivar assigned, there is like just a few of them. There's a bunch of unfrozen strings, and we could probably freeze these strings like by looking at the libraries that don't freeze them and like contributing, which could result in another probably around 10 megabytes of the reduction of the memory of strings. So actually, I think like if you would approach it like from complete point of view, like we could be looking at 30 megabytes, 35 megabytes in total per process, basically. I mean for Puma and for Sidekick, basically. So like probably around 60 to 70 megabytes of the reduction of just the strings deduplication.
And what are those unfrozen objects to save megabytes? I didn't look at the script.
Yeah, so unfrozen objects are the objects that are not frozen. I mean, frozen means
No,
like
I know that, but there is some and to save megabytes.
I'm kind of assuming that the
Results.
bunch of the libraries that we use don't use the frost string literal to true. And this is the reason. I'm not 100% confident of that, but I am assuming that a bunch of these strings can be frozen, maybe half of them. I don't know how much of them. But like there is like 22 megabytes that can be removed of the existing frozen strings, basically. Like just doing an extension to Ruby GC, basically, nothing else.
Okay.
So it seems like, I don't know, probably like if you contribute to the Ruby GC, it would be a piece of code, probably something between 100 to 500 lines of the C code, doing some magic, and that would deduplicate the string that we would reduce about 50 megabytes without any application changes, basically, just Ruby runtime change. I mean, as for me, like, I kind of like continue like with these investigations, like, I'm not sure like where it's gonna like lead me, but I'm just still curious about. Maybe I finally look at this loading of the application and I understand what is happening there.
Sounds good.
Okay, should we stop the recording?